there is an edge out of 1 going to 2, therefore this entry is a 1, right? And no other edges going out of the first vertex. So all other entries on this row are 0. Okay, same way if you follow, 2 has 3 outgoing edges, and so you have 3 ones there. Okay? So that's the representation of matrix representation for a graph. And then we started talking about how once a graph is represented as a matrix, then what do you have? What does it mean, right? So we already see here that if there is an edge between vertex I and vertex j, then aij is going to be 1, right? So for instance, the example I pointed out is there, right? So that is the definition of this matrix. Now what happens when you take the product, right? So what's going to happen is that if you define B as the product of the two matrices, then we said Bij will be equal to 1 if there is a path in the graph of length 2. Right? So there must be some way to Bij will be 1 if there is a k such that aik equals 1 and akj equal to 1. If that is the case, then the product of these two Boolean matrices will have Bij will be equal to 1, right? So we talked about this, right? So you have the ith row in the matrix, and again the jth column, right? So to get Bij, we are going to take this row and multiply it by the entries in this column. And so the moment there is some element here such that the corresponding element over here, if both of them are 1, then the product will be 1. And then when you add up all of the terms, once you get to 1, they're continuing to be 1. So, the moment there is some k such that aik equal to 1 and akj equal to 1, you'll have Bij equal to 1. And what this means is that there is an edge that goes from I to k, and then there is an edge that goes from k to j. Or in other words, you have a path of length 2 in the graph from I to j. Okay? So that's the interpretation when you have when you take a product. Now, if you define C to be A plus B, right? A is the original graph, or original matrix. B is the product of the matrix, right? So A times A. So you add those two. Now there will be Cij will be 1, provided there is a path of length 1 or length 2, right? So Aij will be 1 if there's a path of length 1. Bij will be 1 if there's a path of length 2. So in A plus B, you will have Cij equal to 1 if there is either a path of length 1 or length 2. Right? Any questions? Yeah.
So if there's a path of length 2 and length 1, then Cij will be greater than 1, right?
It's a Boolean matrix.
Oh.
Right? So okay. So this shows what happens for that example graph. A will be this, A square will be this, and A cube will be this. Okay? And now you can define the closure of the matrix as A star equals A power 0 plus A power 1 plus A power 2 all the way. Okay? And since you can either define it as an infinite sum, but typically it's enough to go to a to the power n. Right? In general, once you have a path, if there isn't a path of length n, right, there isn't going to be a path of length greater than n, right? Because it's a graph with only n matrices.
N vertices.
Okay, it's a graph with n vertices. Therefore, the longest path without a cycle is going to be of length n, and therefore there's no need to go beyond a to the power n here, right? Because essentially what a star is going to say is, based on this intuition, you can see that a star is going to be 1 if there's a path between I and j, okay, of any length, then a star of ij will be 1, right? So it's a the closure computation on the matrix ends up being a reachability check on the original graph, okay? So this is reachability, but if you want to talk about shortest paths, okay, then where each edge has a different length or weight, and then you want to find the shortest path, meaning if the path has some number of edges, you take the weight of each edge, add it up, right? So that is, you want to have the minimum weight path, then you can use the same matrix operations, except that you redefine plus and star. So plus becomes, in the Boolean matrix, plus was or, right? And star was and. In the case of, to get the shortest path, then you define plus to be the minimum operation, and star to be the integer addition, right? Because again, if we are talking about edge weights, so suppose aik is 3 and akj is 5, then there is a path to go from I to j, and that path's weight is going to be 3 plus 5, 8. Okay? So this is why the integer, this is why, again, if you look at this, right, so what you're saying is that this has a value 3, and that corresponding element here has a value 5. So in the case of matrix multiplication, we will be multiplying this point by that point, right? And now if we redefine as a integer addition, then we will correctly calculate that this path bij will have 8, assuming that this is the only non-zero entry, right? If there are multiple non-zero entries, then you will take the minimum over all of those, right? So if you think about what happens, so bij will be minimum over 1 less than or equal to k less than or equal to n aik plus. Right? So if you define it that way, then again, just by redefining the basic matrix operations, you can compute the shortest path in the graph without. And now, if you define it this way, now the closure becomes the shortest path, right? So this, if you do a times a, then that'll tell you, what is the shortest path of consisting of 2 edges, right? So this one will tell you, across all of the, so between I and j, there could be a path of length 0, length 1, length 2, length 3, and so on, right? So you will take the path of minimum cost of length 1, path of minimum cost of length 2, path of minimum cost with 3 edges, 4 edges, and so on, and you take the minimum across all of them, right? Because once again, a star, right? Remember that a star is defined as the sum, and in this case, we have redefined plus to be the minimum. Right? So it's going to take the minimum across all paths with different number of edges, and take the shortest, lowest weight among all of them, and that's how this becomes. Is that a question?
Yeah. I'm confused. When you say star becomes integer addition, that means you're treating each of the individual matrix values as an integer and adding them up.
Right. So you have a 3 here, you have 5 there, right?
So then 3 will be added to like the corresponding value in the corresponding.
No, yeah.
Right?
So this will be added to that, right? The second element will be added to the second element here, and so on, right?
Okay.
It's just same usual matrix multiplication. Nothing. The whole idea is not to redefine what it means to do matrix multiplication, right? Otherwise, we shouldn't use matrices if we don't mean the same thing.
So what does it mean star becomes integer addition?
Okay, so in a matrix multiplication, right? So there is a point-wise multiplication that you do, right?
Oh, I see.
Right. So each
It's a field, it's a different
I mean,
field.
you basically like a dot multiplication of these two vectors, right? That's what you do. There's a row vector, that's a column vector, and you take a dot multiplication of those two, right? And that requires point-wise multiplication of each point in the vector, and that point-wise multiplication is being redefined to be an integer addition. Okay? Right. Okay, so why do we, so now that you know this connection, what can you do?
So if we know how to multiply matrices fast, we can find shortest path efficiently.
Correct, right? But usually what ends up happening is that you often know faster algorithms for doing, working on graphs, and you can go back and use that. For instance, if you ever have to compute the closure of a matrix, right? So you can use this to, you can think of it, have a graph interpretation of the matrix and compute the closure in the graph, because you can see that that's connectivity, and it's often very easy to decide, right? So if you have problems that involves matrix computation, especially Boolean matrix computations, or computations on matrices where the operations are defined in this way, then you can see that there is a graph analog, and often the graph, when viewed as a graph, the problem is much more efficiently solvable than computing A star, which seems to require a large number of multiplications, right? So suppose you do, so let's take this, okay? Let's forget for the moment that we know this correspondence between graphs and the matrices, okay? Otherwise, how fast can you compute A star? Okay, assume that you're going to use plain old matrix multiplication, right? So which means you're going to take n cubed time to perform one multiplication. Okay? Given that, how quickly can you compute A star?
N cube, right?
Think about it. Okay? So I'll leave it at that, and we'll come back and pick it up in the next lecture. So think about it, and then we'll talk about it first thing in the next lecture. Okay? So now we have looked at the basic graph algorithms. Now we can resume our study of different classes of algorithms, right? So we did divide and conquer, and the next category of the next sort of algorithm design technique is greedy algorithm. So what is a greedy, or rather, when do you apply a greedy algorithm? So a greedy algorithm is applied for an optimization problem, right? So both greedy algorithms as well as dynamic programming, which is the next unit, both of them are applied for optimization problems, which means that you have multiple solutions and you want to find the best solution. Okay? Now, so what is a greedy strategy? Greedy means you try to optimize locally, right? So that's the meaning of greedy. So given the information that you have, what is the best next step based on the information that's available right here and now, right? Instead of having to look forward into the future, you just look at it at this point in time and make a locally optimal decision. And as you've heard many times, locally optimal is often not globally optimal. So whenever you use a greedy algorithm, right, you should try to prove that the greedy choice, in fact, leads to an optimal algorithm, right? It is not to say that you never use non-optimal greedy algorithms, right? So there are problems for which you don't have a better choice, and you just can use a greedy algorithm which is known to be non-optimal in general. But ideally, right, so you would have a greedy algorithm which is also optimal, and in that case, you want to prove that it is optimal. So the point is that if an explicit proof is required because greedy algorithms generally, right, are not optimal. So if you have to do the hard work of proving, well, proving is a one-time task. But if the algorithm is simple enough, greedy algorithms tend to be quite simple. If the algorithms are simple, then you get the benefit of working with a simple algorithm, and therefore, if you can design a greedy algorithm, you would, of course, prefer to do that. Okay. So let's take a very simple warm-up problem, right? So you want to make change, right? Given coins of various denominations, make change for an arbitrary amount of money, right? So x for 0 less than x less than 100, right? So here is a greedy solution, right? So it's greedy because you pick the largest denomination that's smaller than the change that needs to be made, right? So it's greedy in the sense that you want to, your goal here, right, is to make change with the smallest number of coins, right? Otherwise, you can always give out pennies for everything, right? So that's obvious, and we are not interested in that. So we want to try to make change while having the smallest number of coins we can. And a greedy way to do that is to say, okay, let me try to give out the biggest coin I can, right? And then hopefully that'll minimize the number of coins that I hand out. Okay? So let y be the largest denominator that satisfies y less than or equal to x, and issue x divided by y, the floor of that. So for instance, if you have 77 cents to pay out, then the y here will be 25, right? So x divided by y floor of that will be 3. So you will start out by giving 3 25-cent coins, right? And then now out of 77, you're given out 75. So you have 2 more cents to give out. So you're going to make change for that amount, right? 77 mod 75 is 2, and you're going to call yourself recursively to make a change. Make change for the remaining amount, right? So you hand out 3 quarters and 2 pennies, and then you're done, right? So now the question is it an optimal algorithm? so either it is exceptionally obvious or
No, yeah, definitely.
okay. So this is the interesting question is it optimal for all denominations? That is, in this particular case, 25, 10, 5, and 1, right? This algorithm is optimal. Okay? So, when you apply this, for instance, to affixing stamps to a piece of mail, right? So, you want to, somebody tells you this much is the postage, and you buy stamps and fix them, right? And let's say you have lots of stamps of all possible denominations, right? Meaning in all denominations that stamps are usually sold, right? And in fact, they probably don't sell stamps that way anymore. So you probably have to go back to when you are in elementary school or something to know how many different denominations they used to sell stamps. And then the question would be whether, in a case like that, if this algorithm is going to be optimal or not. Okay. So is there some condition under which this is optimal, and is there some condition under which it's non-optimal? Yeah.
Yeah, I mean, if you start off with the largest denomination, it's possible at some point you'll be stuck in a state where you can't use the other currencies to actually do it properly.
Okay, so let's not worry about so much about that, right? Because you can always have one cent things, right? So you will never run. It's not a question of not being able to make a change, but just a question of whether it's optimal or not, right? So let's say you have you add to this, 3 cents. Okay. So then, is this algorithm optimal? Let's just make that one change, right? So we add 3 cents.
By comparison. 22, 21, 1, 2, you had 20, 11, and 1, 2. The VD source is not low.
Well, you can correct me if I'm wrong, but I think 3 cents doesn't cause a problem. I think it is still optimal. What about 4 cents? Okay, I add a 4 cent
Yeah.
to this list.
Yeah, that
Is it still optimal?
No, it won't be optimal.
Give me an example,
8.
right? So when you have 8 cents, the greedy algorithm will first give out 5, and then it will give out 3 pennies, right? Whereas a non-greedy technique would correctly realize that there are 2 4-cent coins that you need to get, right? So this is optimal only under certain conditions. Okay? So again, I want you to think about what is the condition under which this is optimal. Okay? So let's see if someone can come up with an answer by the beginning of next class. Right? Okay, so now we'll talk about, now we have at least a basic sense of what a greedy algorithm is. So let's try to understand some of the reasons, some of the conditions under which greedy algorithms work, right? So, so a greedy algorithm is again, whenever we use a greedy algorithm, we always, by default, we think, we are using it because it does produce the optimal solution, right? So it's sort of it's uninteresting to talk about the cases where you use a greedy strategy but it's not optimal, right? So that you can always do that, and it's not, nobody has to tell you that this is a design strategy that you can use, right? So the greedy choice property basically is there to ensure that a locally optimal choice also is a globally optimal choice. Okay? So if there is a problem for which a locally optimal choice will also be a globally optimal choice, then of course a greedy algorithm is appropriate for that problem. Okay? So once again, you might want to think, what does this mean for the coin change problem? And maybe that will tell you how to identify the conditions under which the coin change problem, the conditions under which that greedy algorithm is optimal for coin change. Okay. The second thing that you want in a greedy algorithm is an optimal substructure, right? Because what that means is that you can use this algorithm recursively. So you make a locally optimal choice, right? And then so you compute essentially the next step in your algorithm. And after figuring out that next step, then you would like to use the algorithm in a recursive way to get through the rest of the way, right? So that is the optimal substructure problem, which basically says that at every step, if you choose make an optimal choice, then you will ultimately get to the final optimal solution. Okay?
Can you show the denominations for that?
It's there on the
1, 5, 10, 25.
You only have to do it by the next lecture, and it's there on the. Okay, so let's take another simple problem, right? The knapsack problem. So what's the knapsack problem? You have a sack that has a certain capacity. So in this case, let's say the capacity is based on the weight you can carry, and you have some choice of items that you can pack in the sack, and you want to maximize some value. Right? So in this case, let's say you're going out on a wilderness trip, and you can only carry so much, and you want to maximize the calories so that you can stay there for as long as you can, right? So you're given 4 items that you can pack: bread, which is 1,100 calories per pound, and you have 5 pounds of it. Butter is 3,300 calories, and you have 1 pound of it. And tomato is, the vegetables, of course, not many calories, and you have a few pounds of it, right? So now, let's say somebody tells you, how to optimize this, and then there are 2 kinds of knapsack problems, right? So there's a 0-1 knapsack, which means that you can either pick an item and take it in its entirety, or you can leave it out. Right? So that's why you have a 0 or 1 choice. Right? So you can say, you can choose to take all of the bread or none of it. Right? Or you can choose to take all of the butter or none of it. Right? A fractional knapsack is a case where you can, cut a piece of it and take it. Right? So for instance, you can say, in the fractional knapsack version, you can take, half a pound of butter and half a pound of bread. Right? Whereas here, in a 0-1, you would either take all of the bread or all of the butter or all of both, right? So you cannot have anything fractional. Okay? So given this knapsack problem, once again, it's pretty clear what a greedy choice would be, right? So greedy choice would be, you pick the item that maximizes the calories per pound, right? Because you want to reduce your weight as much as possible and increase your calories as much as possible, which means that you want to optimize or maximize calories per pound, right? And if you use this choice and you have actually a fractional knapsack problem, then this problem can be solved using a greedy strategy. Okay? Say, for instance, you can carry up to 5 pounds. The greedy choice will, let's see what I have here. So the greedy choice says maximize the calories per pound, which is maximized for butter, right? So you're going to take as much of the butter as you can. Well, you can carry up to 5 pounds. There is only 1 pound of butter, right? So you'll take that 1 pound. Now you have 4 more pounds that you can carry, and the butter is used up. You have only these 3 quantities, so you can recursively apply the same algorithm, and that'll pick. Okay, now calories per pound is maximized for bread, and you can take 4 pounds of that bread, right? And then you're done. Okay. Obviously, if you're dealing with a 0-1 knapsack, the greedy choice won't work, because the greedy choice will pick butter, and then, well, you have more capacity to carry, but the bread is too much, so you cannot go to bread at all. You have to only take butter and then vegetables, and that's obviously not going to be a good solution. Okay, so again, fractional knapsack problem can be easily solved, but 0-1 knapsack is a very hard problem, right? So later on, when we talk about empty complete problems and so on, you'll see. We will look at this class again. Okay, so but let's try to understand what these 2 properties mean, right? Greedy choice property, right? So we want to show that for the fractional knapsack problem, the greedy choice property holds, right? And usually you prove the greedy choice property by contradiction, right? So you start by assuming that there is a solution that does not include the greedy choice, right? So for instance, in this example, okay, again, for the fractional knapsack case, let's assume that you somehow have a solution which doesn't include butter, right? So you make that assumption, and then you're going to prove by contradiction that that is not possible. And how do you do that? You basically are going to say, look, I have 1 pound of butter. So what I'm going to do is, the so-called optimal solution, you give it to me. Out of that, I'll cut out 1 pound and throw it away and put the butter back in there, right? And obviously, since butter had the highest calorie per pound, now after this replacement, I should have more calories for the same 5 pounds than what I had before, right? So obviously, there is a contradiction. I couldn't have had the optimal solution before, right? So that is, again, this greedy choice property is particularly easy to prove for this problem. That's why I'm using it as a warm-up problem for greedy algorithms. Okay? Yeah, once again, the property doesn't hold for 0-1. So now let's talk about something that's more interesting and more significant, right? Spanning trees. So what is a spanning tree? The spanning tree consists of a subset of edges in a graph that is actually a tree, right? So you throw out edges such that until you no longer, until you have just a tree and you don't have any other additional edges, right? So the spanning tree must have all of the original vertices in the graph, and it has a subset of the edges such that these edges form a tree. Okay? So for spanning tree, the problem is defined for directed graphs as well, but it is a little bit hard to understand, and the algorithm gets quite complicated. So usually you study spanning trees on undirected graphs. Okay? So when we say that something must be a tree, right? So a tree has many properties, right? So a tree has no cycles, right? Obviously, and a tree with this many vertices has that many edges, right? So n vertices, if the tree has n vertices, then it must have n minus 1 edges, right? So this is another property of tree, okay? Provided it's connected, right? So it's not just that you pick any subset of n minus 1 edges and you have a spanning tree. Well, you may have disconnected components and then it's no longer a tree, right? So everything should be connected. So if you have a connected subgraph that has n minus 1 edges, that will be a spanning tree. Okay? So finally, a third way to talk about is that it's a subset of E such that there is a unique path between any two vertices in the subgraph. Okay? So these three conditions are all equivalent. Okay? So for instance, if there is more than one path between two vertices, right? That means there's a cycle, right? So anything that satisfies this, anything that violates this will also violate this, and so on, right? So you can think about it and convince yourself that these three conditions are all defining what it means to be a minimal, what it means to be a spanning tree. Okay. So what is a minimal spanning tree? A minimal spanning tree is one which is where the edges have weights, and then you choose a subset of edges such that the total weight of the tree is minimized, right? So, for instance, if this is your initial graph, then the minimum spanning tree is this. Okay, so it tends to use the, for instance, it doesn't include this edge, which happens to have a high cost, this edge, which happens to have high cost, and so on. Okay. On the other hand, to connect E and F, this is the only possible edge, right? And to connect C and F, this is the only possible edge, so you have to choose them even though they seem to have a somewhat high cost. Okay, so there are two algorithms for constructing minimum spanning trees. One of them is called Kruskal's algorithm, and the other one is called Prim's algorithm. They are in some ways mirror reflections of each other, or complements of each other. One of them starts with the Kruskal's algorithm starts with an empty graph and then adds edges from their smallest cost, right? So you start with an empty edge, add the lightest edge that doesn't create a cycle, right? And then you keep doing that until until basically you have constructed a tree, right? The Prim's algorithm goes in the exact opposite way. It starts with all the edges in the graph, and then it starts removing the edges from highest cost first, right? It's going to pick the highest cost edge, try to remove it, and see if the graph still remains connected, right? If it remains connected, then you can remove them. Then pick the next highest cost, again do the same thing, and you keep going down until you have a tree, and then once again that'll be. But we'll only talk about Kruskal's algorithm in detail. So the algorithm is very simple, right? I'm not even going to talk about it, give it an algorithm form, because all you do is you pick the lightest edge that doesn't create a cycle. Okay? So that means you're going to pick. So out of all the costs, you see that this is the first cost. Let me see if I have an animation of this in the next. Okay, so let's go through this, right? So we are going to right? So there's some edges. You're going to pick the minimum cost edge. So that is going to be that, right? And now we look for the next minimum cost. You have a choice of C to D, right? So since C and D are not already connected, we will connect that, right? Now the next minimum is 2, right? But you can see that B and D are already connected there. Therefore, this edge, if you add it, then it will form a cycle, right? So it's no longer, shouldn't be part of the spanning tree. So then you look for the next lightest, that's going to be 3, right? Now C and F are not connected, so you're going to connect them. Okay? And then the next one is 4. So you can either choose okay, D and F are already connected, so this edge is not, you can't use this, but you can use this edge, right? And now there's one more, which is between A and D, right? And A and D are not connected. And at this point, everything is connected, right? So you have constructed the minimal spanning tree, right? The minimum spanning tree. Okay, so it's a very simple algorithm, right? So so let's now provide some of the details. So you can see that you need to pick the edges from lowest cost to highest cost, right? So it makes sense to use a priority queue data structure for the edges, right? So you take the edges, you arrange them into a priority queue so that each time you remove it, you can do that quickly. Okay. So you're going to pick while Q is non-empty. Q consists of all of the edges, right? While Q is non-empty, you can delete min if E connects two disconnected components. Only then you're going to add it, right? If the edge connects two vertices that are already connected in the spanning tree, then you don't add it, because if you do that, then you'll create a cycle, right? So you're going to pick the minimum, see if it connects disconnected parts of the graph, then you'll add that. If not, you will not bother with that edge and more, right? So although this says while Q is non-empty, you can also stop the moment you create a tree, right? So once you've created a tree, then you can stop. Or in other words, once you've added n-1 edges, right? So you can stop. You don't have to continue after that. So so let's do the proof next time. Okay, so let's look at the complexity, right? So each DQ operation, right, takes log of the size of E, right? Because it's a heap data structure we are going to use. So the DQ operation takes log n on heaps. So the number of edges is given by, the number of elements in the queue is given by the number of edges. Therefore, each delete min operation is going to have the cost log E, and that log E, right? So E right? So the number of edges can be at most square of the number of vertices, right? In a graph. And therefore, if you take log E,